Hello viewers, in the last couple of lectures we have discussed the instruction set of microprocessors, which we may consider as the vocabulary of the machine, and using those instructions as the basic elements, the user has to write program. Now today we shall discuss an important topic, that is assembly language programming. You may be asking, why assembly language programming and what is it? Let us discuss the first question, why. As you know, the machine that you are using, the microprocessor, is nothing but a machine. That machine understands only machine language. So if the program is written in machine language, that is best for machine. Unfortunately, the programmer or user is not familiar with machine language, and obviously writing program in machine language is extremely difficult by a programmer or an user. Obviously, English is the natural choice for a programmer or a user. That means for a programmer or an user, the best choice will be English. So English is best choice for programmer and user. Machine language is best choice for machine. Obviously, we can there does not exist a computer or a processor which understands English. Although in science fiction books or movies, you may have seen that the user is giving comments in English and the computer or robot is understanding it and so on. But in general, it is not possible for a general purpose computer to understand the English as the basic language. So some alternatives are used, something in between. For example, for the convenience of the human user, high level language such as BASIC, Fortran, C are commonly used. These languages are known as high level languages, although these languages are not as natural as the English language, but these are closer to English language. That's why these languages are called high level language. On the other hand, if we go one step ahead from the machine language, we have already seen that mnemonic language, mnemonic machine language, that can be used. And we have already given an example for that. For example, this is the machine language, and this particular program written in this form is known as mnemonic machine language, where each instruction, as you can see, is represented by mnemonics. And we have already discussed the advantage of using mnemonic machine language, because each operation specified with the help of a mnemonic is self-explanatory. It tells what it will do and so on. As a result, it is very easy by a human user to understand what the instruction does, and obviously writing program is more convenient by using mnemonic machine language. However, there is another extension of this mnemonic machine language is assembly language. So assembly language can be considered as an extension of this mnemonic machine language. And obviously, the mnemonic machine assembly language will have more or less one-to-one correspondence with the machine language, as we have done in this particular case. Each mnemonic machine instruction is replaced by machine language instruction, is corresponds to a machine language instruction. So more or less same thing will be done, but something more. And obviously it has got a number of advantages, and in this world nothing is one sided, it will have some disadvantages. So we shall discuss these advantages and disadvantages, and then discuss in detail how the assembly language program is written. Let us look at the advantages. First of all, it is better for human understanding. As I have told, it uses the mnemonics. So obviously it is much closer to the English language, and as a result it is better for human understanding, and it is made more better by using, as you have seen, it uses mnemonics for opcodes. So operations are easily understandable by the human user. Second advantage is, another important feature is the use of symbolic name for operand address. In the program that we have shown here, for example, this address or this address is given in absolute form. That means absolute address is provided as part of the instruction. So whenever absolute addresses are provided, it is very difficult to keep track by the human user. So these operand addresses are replaced by some symbolic name, and this also improves the convenience of the programmer or the user. Obviously, writing program in assembly language is more convenient, easy than writing program in machine language. It can be easily modified, because whenever you modify a program, you have to insert some instruction, you have to delete some instructions. Whenever you do such insertion and deletion, obviously if it is written in machine language, you have to do it yourself. But whenever you write program in assembly language, whenever you modify a program, the assembler, as we shall discuss later on, will take care of that modifications automatically. I mean, in a very convenient way, you can insert some instruction, you can delete some instructions, and automatically the later part of instructions will be adjusted by the assembler, as we shall see later. So it is very easy to write program, modify it, and debug it. As we shall see later on, a program, whenever you write, may not work in the first instant, may not run. So there may be some bug, and debugging is very convenient whenever you write program in assembly language. And as we shall see, the assembly language program is self-documenting. Documentation is very important for maintenance, for future maintenance and debugging. So assembly language programming inherently provides self-documentation feature. Then whenever you write assembly language program, it checks the syntax errors, because you will see a software will be used to convert the assembly language to machine language, and that will automatically check the syntax errors, and so some of the errors will be detected by the software, by the program, by some program and computer, and so errors will be, some of the errors will be eliminated whenever you write in assembly language, and you will be able to reserve some memory locations for data very easily by using assembly language. Another advantage which I did not mention here, it provides you more efficient program. It has been found that whenever you write a program in, say, assembly language, as I have told, if you can use, one choice is you can write program in BASIC, Fortran or C. Whenever you write a program in high level language, that high level language program has to be converted into machine language with the help of compiler. The compiler generated code has been found to be not very efficient compared to a program written in assembly language. In other words, whenever you write a program in assembly language, the code becomes very efficient. That's why very important programs like systems programs, assembler, loader, linker, and some parts of the compiler and some parts of the operating system are written in assembly language, because assembly language program leads to very efficient code. That means the program will require lesser area in the memory. It will take lesser time to execute. So that is another important feature of assembly language program. And obviously these advantages uh, have led to a led to the use of assembly language program very widely, and particularly the application domain for which we are looking for, particularly for embedded systems. You will be writing not very big programs, not very complicated programs, but the programs have to be very efficient, and these programs must be stored in ROM, and most natural way of writing program for these particular applications is in assembly language. That's why we shall discuss in detail the writing the way you can write program in assembly language. Obviously, as I told, in this world nothing is one-sided. It has got some advantage. The uh, the most important disadvantage is that you will require a piece of software known as assembler. You will require assembler to convert the program written in assembly language. You have written your program in assembly language. That program has to be converted into assembly language into machine language with the help of an assembler. That means this assembler converts the assembly language program to machine language program. So this machine language program conversion will be done by a software. So unless you have the software, you cannot write program in assembly language. So it is very important to have an assembler, and obviously this assembler will be dependent on the processor. In case of high level languages, you may have seen that compiler, if the program that you write is not specific to a particular processor, that C program is independent of the machine. Assembly language is not so. It is specific to a particular machine. So assembler also will be specific to a particular machine, and that assembler must be available to you. So whenever you write program in assembly language, that program is known as source code. Source code, and that is used as input to the assembler. The assembler in turn produces machine language program which is known as object code. And obviously the source program, source code has to be written in such a way that assembler can translate it into machine language. In other words, this is a very important restriction. The source program or the source code must be written in well-defined format for easy translation by assembler. In other words, what I am trying to tell, it imposes some restriction on the way you have to write program in assembly language. You have to write program in a very well-defined way so that it can be very easily understood by the assembler, and assembler can convert into machine language. In other words, the complexity of the assembler has to be reduced by writing in a well-defined format. Let us see what kind of format is used for writing assembly language program. Assembly language program has 4 unique fields: label, usually it is separated by a delimiter colon, then the operation to be performed with some gap, operands, there may be one or more operands. Then you have another field for comments. What is the purpose of the label? Purpose of the label is uh, it provides you the symbolic name of address. As we shall see later, in the label field you provide the symbolic name of address where the program will jump, or which you have to refer in your program as part of the instruction. Obviously, it can be represented with the help of a variable number of characters. A number of characters can be used to represent a symbolic name, and a label may be present, may not be present. So it is not always present. In other words, each line of instruction may not have a label, particularly if you don't have to refer to it, there is no need for it. Then comes the operation field. Operation field will you have to provide the mnemonic of the opcode. As you have seen, each and every instruction performs some operation, and that is represented by the opcode, and the mnemonic of the opcode will appear in the operation field of the assembly language program. Of course, apart from the machine language opcodes, you will see sometimes you require some opcodes which are not meant for the program, not meant for the machine, but for the assembler. That means these are also known as assembly directives. So some commands are provided which are meant for the assembler, and those are known as pseudo opcodes. We shall discuss about these pseudo opcodes. And of course, there are another feature which are available in some assemblers, which is known as macro. So if some part of the program appears repeatedly in a program, that can be replaced by a single line of code known as macro. And whenever a macro facility is provided, it is known as macro assembler. But macro assembler may not be always available, so this we shall not discuss. But in some assemblers, this macro facility is provided. Then comes the operands. In the operands fields, as we know, whenever you perform some operation, it will involve some operands, one or more. And operand field specifies the operands. Operands separated by comma. So comma is the delimiter for, say, between two operands. Whenever you have only one operand, there is no need for comma, but whenever you have more than one operand, it is separated by comma. Finally, there is a field called comments. In the comments field, which is separated by a delimiter semicolon, and this comments field is used to writing your comments so that the programs become self-documenting. As I was telling, that assembly language program has built-in feature for self-documentation, and so with the help of this comments field, you can make it self-documenting, and particularly for easy understanding for easy understanding of the program, and as I said, for future maintenance and for self documentation. So with the help of these 4 fields, you can write a program in assembly language. Let us discuss about the particularly the pseudoops, pseudo opcodes. There are few pseudo opcodes which are available in all assemblers. You will see that assemblers are available of different capabilities. So assembler feature of for a particular processor may be different from the assembler feature for another processor, but there are some commonalities. So I shall discuss the most common pseudo opcodes which are available in assemblers. One is ORG. With the help of this ORG, the origin of the program or the starting of address of the program is specified. So for example, if you want to start your program from E000 in hex, so in the opcode field you have to write ORG, and in the operand field you will write E000H. So this is the pseudo opcode. So obviously ORG is not an instruction for the machine language. It is not a machine language instruction or mnemonic of a machine language instruction. This is a directive to the assembler. Assembler will start generating machine language code starting with the address E000 whenever this ORG pseudo opcode is provided. Another pseudo opcode is EQU, equal. EQU stands for equal. So in the label field you will write something, say ADDR. In the operation field you will write, say EQU, and in the operand field you will write some value which you want to make equal to this particular symbol, the symbolic address or symbolic data. Say it can be a symbolic name for address or for data which you want to make it equal to some value, and that value you have to specify. For example, this is an address, so the value of that address is 003A, and with the help of this pseudo instruction that can be specified to the assembler. Another is DB. With the help of DB you can reserve several instructions. For example, data is the label field, then DB is the in the operation code field, and then you have to provide some data. Yes. So until you finish, so each of these data will be stored in a memory. You are allocating a memory space for this data, for this data. So an array of data can be stored in the memory, and memory allocation is provided with the help of the pseudo opcode DB. So these are the most common pseudo opcodes, but as I have told that availability of pseudo opcodes will vary from assembler to assembler. So whenever you go for using a particular assembler, you have to become familiar with the pseudo opcodes available for that particular assembler. Now I think we should illustrate the use of assembly language program and how you can write an assembly language program. So you have to write program in source code. The program which we have shown in the beginning, this particular program, I am writing this program itself in assembly language, and it will look like this. Say I give a comment. First I give a comment that this is a simple program example. This is a comment because it has started with the delimiter semicolon. Then in the next line I have written OP1 operand 1 equal to say 003A. Essentially, I am trying to provide the operand address for the operand 1, and the address is provided here. Similarly, OP2 is equal to OP1 plus 1 next address. OP3 operand 3 is equal to OP1 plus 2, and then I use that pseudo opcode. These are all pseudoops. ORG, say I want to start my program from 3000 memory locations, and then starts your assembly language program. Load OP1 from operand address 1, and obviously I shall write some comments. Loads operand 1 in accumulator, then move BA, and it moves the operand to accumulator. LDA operand to load operand from operand address 2, so it loads operand 2. Then he will perform the addition. Here it loads the operand in accumulator. He will do addition. Add B. Already your one operand is in B, and so another operand in his accumulator. So you will perform the addition. So you will write addition of the operands. Then you will store the result in the memory location operand 3. So it stores the result. Then of course you have to end your program. I use writing a pseudo opcode halt, not pseudo opcode, operation code halt. So this is the program you will be writing in assembly language, and then you will give it to the assembler, and assembler will translate it into machine language, and it will generate the two fields, location and object code. Location and object code. So this will be converted into 003A. That means operation 1 is equated to this, then 003B and 003C. Then your program will start from memory location 3000, and code for this particular instruction is 3A00, because operation this OP1 value is 003A, first the lower order byte followed by this higher order byte, and then it will occupy 0, 1, 2. So next instruction will start from 3003 memory location, and code is 47. Then 3004, next instruction 3 this is also a load instruction, so this will be 3A and 3B00, because here it uses the operand 2 address, which is equal to 003B. Then this will occupy 4, 5, 6. So next instruction will start from 3007 80. This is the code for this add instruction 80. Then it will next instruction will start from 3008 32 3C 00, and then 3009 memory location will occupy 76. So this is your machine language code. So if you take a listing, program listing from the assembler, you will get this kind of listing where the source code and object code will be provided, and some assemblers will provide the line number for easy debugging, 1 2 3, for modification 4 5 6 7 8 9 10 11. So 11 lines of assembly language program, and for example you want to modify this, then by using the line assembler line number, the you can do the modification of the program. So this is how the source code is provided. Assembler then you apply it to the assembler. Assembler generates the object code, and you can get a listing like this. Now you have got your machine language program. Either you can enter it by hand into the computer, or electronically also it can be transferred to the computer, to the processor in which you want to execute. Now this particular process of writing a code is known as coding. This step is known as coding. You are writing program in assembly language for a particular processor, and this step or this phase is known as coding. But coding starts much later in a software design cycle. Whenever you are designing a software for a particular application, you have to start with more with the problem specification. And as you know, software design is considered to be an art. You cannot specify with the help of some deterministic rules that you follow these steps and your program will be very efficient. You can't say that. However, you can follow some techniques, use some tools and techniques, follow some steps, so that ultimately your program will be easy to understand, maintainable, easily debuggable, and so on. So I shall tell about those principles or steps that you have to follow to write a good program. So we can call this as software design steps. Software design steps starts with problem specification. So problem specification is a very important step, and in the problem specification step you have to specify the problem in a very unambiguous manner, so that the problem is clear and you can write the algorithm or the next steps, and in the way you will implement it. So problem specification is very important, and you have to specify the problem without any ambiguity, in a clear language. Usually problem specification is stated in simple English. Then you have then you have to start the design step. What will you do in the design step? In the design step you will obtain the structure of the program you will design. Now in some cases the problem may be very complex. If you write a single program, a monolithic program, it may be too big, too complex to debug. So what is being done? Some top-down design approach is followed. Top-down approach. So in the top-down design approach, you divide the problem in terms of few simpler sub-problems. Then again each sub-problem is divided into few simpler sub-problems. It is like divide and conquer approach, and this can be represented with the help of a hierarchical diagram. So hierarchical diagram will tell you the the modules and submodules. In other words, uh, the concept of modular programming goes hand to hand with this top-down approach. Modular programming. You have divided a single problem into a number of modules. Now, whenever you do this, what essentially you have done, you have divided a single problem, a single task into a number of subtasks, and each of these subtasks can be independently, you can write program independently, you can debug them independently, but ultimately you have to put them together. How will you do? How assembler will do? So for that purpose, the approach will be somewhat like this. Say this is your module 1, module 1, module 2, module 3. So each module will be written in assembly language, and you have to apply it to the assembler. So this will go to assembler. Each of them will be separately applied to the assembler and assembled separately. Then the assembled program is linked with the help of a linker. The symbolic addresses generated by each of these assemblers will be linked with the help of a linker. And after all these programs are linked together, it will be loaded by another piece of software known as loader. After this is done, the object code that is generated will be loaded in the main memory. As you know, to execute a program, the primary requirement is that the program has to be present in the main memory. Must be present in the main memory. So your module 1 will be loaded, module 2 will be loaded somewhere in the main memory, and module 3 will be loaded in the main memory. Now module 1 may be the main program, and module 2 and module 3 may be the subroutines. So module 1 will call this subroutine and will call this subroutine. Now these call addresses are linked with the help of this linker. That means after this loading is done, the program can be executed. All the three modules will interact with each other and program can be executed. So this is how a big program, a big task can be implemented in terms of modules. And after you have divided into each module that specification, you will be doing the coding. And obviously coding is the best understood step of the software design, and this is where the machine dependent or language dependent step starts. Prior to that, that means problem specification, design, these two are usually machine independent or language independent. On the other hand, coding is machine dependent as well as language dependent. Then comes after the coding is done, either in our case in assembly language, you have to do testing and debugging. Obviously, after you write a program, you should not expect that it will be bug free. There will be some bug, and you have to debug it. And for that purpose, some tools and techniques are available, which you will use later on when we shall discuss microprocessor development system. We shall discuss in detail the various tools and techniques available for this purpose, but some of the tools and techniques you may be aware of. For example, single stepping. Single stepping you can do, you can execute one instruction at a time Then you can find out the content of registers, content of memory location, and check whether the particular instruction has done the desired operation or not. Another tool is use of breakpoint. At some key positions of the program, you can put breakpoint. So up to that part of the program, it will execute without any interruption, without any gap. And after executing that up to that particular breakpointing point, the programmer can check whether the register contents, memory location contents are as desired or not, and find out whether it has run correctly or not. And whenever we shall discuss the microprocessor development system, a more sophisticated tool and technique called in-circuit emulation that can be used. Later on we shall discuss about it. And finally comes the question of documentation. Documentation is very important. Documentation is very important for future maintenance and debugging. For example, somebody has written a program and he has left the organization. Some lurking bugs will pop up maybe after a few years. So to modify or correct that particular bug, a nicely documented program is necessary. So the documentation has to start from this problem specification step. While designing, while coding, while testing and debugging, each and every step you have to do the documentation so that you can maintain it. So that's why documentation and maintenance. These two go more or less hand to hand. That means you have to do the documentation properly so that it can be easily maintained in future. It can be, for example, a particular program was written some time back and it is not satisfying the present day requirement. It is necessary to modify or enhance the program. So that enhancement can be done if the program is properly documented, so that a successor, the person who may not have written the original program, can extend it, can modify it. That should be possible. Now, particularly when you are doing the design and before the coding starts, one important technique that is used for documentation is known as writing the representing the structure of the program is called flowcharting. A flowchart is usually used to document or specify the algorithm, or you could to document the algorithm. Flowchart is used, and flowchart represents the program in a pictorial form with the help of few symbols. These are the symbols used, and the meaning of each symbol I shall write here. For example, an ellipse. Ellipse is used essentially for termination. For example, the start, end, this kind of termination of the algorithm is specified with the help of this particular symbol, ellipse. Then parallelogram is used to specify the input and output. Inputs and outputs are specified with the help of this particular symbol. Then a rectangle is used to specify normal program sequence. Normal program sequence can be provided inside such rectangles. A sequence of instruction execution will take place to implement a particular task. Then for decision making, this diamond either this shape or this shape is used for decision making. Diamonds are used for decision making. Then you have got continuation symbols. With the help of which you can suppose on a particular page you are not able to write the flowchart. So you want to continue to the next stage, that can be done with the help of these continuation symbols. And you can write some number inside it, say 10, and where the next one will start you can write tens. That means these two are the same points of the program. Then of course you have to specify the direction. So direction of the program execution. Program execution can be specified with the help of these direction symbols, arrows. So let us illustrate this with the help of an example. We have already written this program, this particular program. But before you should have written this program, you should write the flowchart of this particular program to specify the algorithm or the systematic step for implementing the program. In this particular case, it may be trivial, simple, but it will represent how it is being done. For example, you will start with that start symbol. Then the next step is you have to load operands from memory to registers. This is the first step you have to perform with the help of some steps. Then your main job in this particular program that you have already discussed, add operands. Another step. Then you will do store operands, store result, not operand, result in memory. That is the last step of your program problem, and the end will come here. So in this particular case, the problem is very simple. There was no need to use either this parallelogram, because there was no input from input output devices. Also there was no need to use this continuation symbol, because it was possible to accommodate the program on a single page. So you see, we have written a simple flowchart, example flowchart for a particular program. Let us take up another example where the other symbols like parallelogram, diamonds are being used. We consider a very real life problem with this problem specification. Read data from a temperature sensor. The sensor is connected to port 1 and make a relay on which is connected to port 2, and to make the relay on you have to output 01 in hex if the temperature data is less than equal to 7F. In other words, if the temperature data is less than 7F, we are making a relay on. If the temperature data is more than 7F, we do not make the relay on. This is the problem, and let us do the design. Design is done by implementing a flowchart, as I explained earlier. So it starts with a start symbol with a elliptic symbol for it, and then you have to read data from port 1, which represents the temperature sensors data. So you have to read data from port 1. This is so here this is, since this is a reading from some input output port, this will have the symbol, of a parallelogram. After it is the data is read, you have to check whether it is whether the data is less than equal to 7f. If the data is less than equal to 7f, if the answer is yes, then you will output 00 to less than 7f means you have to output 01. You have to output 01, or let me make it no to make it simpler. Output 00 to port 2, because the relay is connected to port 2. Then if the answer is yes, if the data is less than equal to 7f, if the data is less than equal to 7f, then you have to output output 01 to port 2. So here you see both the cases, these are output symbols, and here is a diagonal for decision making, and we are putting a continuation symbol here, although we could have directly connected. Just to illustrate the continuation symbol, in both the cases inside the circle we write 1. That means this is connected here. And then in both cases, after performing this output, it comes to stop. Here we stop. This is the flow chart. Then we do the coding, write the program corresponding to this flow chart. This reading of data can be performed by simple in port 1 instruction. You can put a comment, read temperature data, temp data. After you have read, you have to perform the read operation. You have to compare this with 7f. So you input the value 7f, then perform jump operation to say loop 1, which will point out that thing, loop 1. That means here compare and jump to relevant position. Now here in this part, what you have to implement, you have to output 01. So MVI 00H, and however we would like to do this one first. Say L1, whenever you, or in this case you have to output 01, so L1 we put the level here, then we write MVI 01 in this case H. So and then you output this data to port 2. What do you want? In both cases, this data as well as this data, either this or that data has to be outputted. So here you have to put one instruction, jump, unconditional jump to L2. So here we put L2. So this part is implemented with the help of this instruction. This part is implemented by using this instruction, and then you have to end the program with halt instruction. So program stops here. So here you are reading you are outputting output 0 1 0 0, and here you are outputting 0 1 to make relay on. So these are all we are using, these are as comments. So we have used comment fields and then the coding. Here we see these two parallelograms are representing input, and this is a diamond box which is representing decision making, and here you have used the continuation symbol, and these two are essentially start and end symbols. So this illustrates how the how a flowchart can be used to represent a decision making and also input output. Now in this lecture we have not considered looping. If necessary, you can do the you can continuously read the data and do the looping, that we shall discuss later. Now let us summarize what we have discussed in this particular lecture. We have introduced to you the assembly language programming, the relevance of assembly language programming, why it is needed and what are the advantages. And obviously whenever you use assembly language programming, you have to use an assembler to convert your assembly language program to machine language program. Then we have discussed the assembly language format. Unless the program is written in a proper format, it will be difficult by the assembler to translate it to machine language. That's why you have to do you have to use proper format for representing assembly language. We have also introduced the concept of pseudo opcodes. These pseudo opcodes, as I told, are essentially directives to the assembler. These are not really the instructions of the processor, but they are used to give some directive to the assembler. For example, org, db, these are the pseudo opcodes which have been introduced here. Then we have discussed software design concepts which are important for writing reliable, readable and easily testable program. And we have also introduced another very important concept, that is flowcharting. With the help of the flowchart, the flow of a program can be very easily represented in a readable form. So in a pictorial diagram, you can represent your design with the help of the flowchart. So you have illustrated the flowchart. So in the next lecture, we shall discuss two very important topics of assembly language programming, or in general programming in any language that is necessary. One is program looping. As I mentioned little few minutes back, so we shall discuss program looping, and we shall also discuss subroutine linkage. These two topics we shall discuss in the next lecture.